Welcome to this lecture on statistics for high-throughput experiments. I'm Lucas Schell and I'm at the School of Biotechnology of KTH. As we move from the word of single readout experiments to high-throughput experiments, the notion about what quality metrics to report for the experimental readouts changes. This got to do with the numbers of observations that we make in each experiment. In typical high-throughput experiments, we make thousands or millions of readouts, and in this setting, unlikely or rare events become quite likely. And for instance, what we call a once-in-a-million experience in a single readout experiment actually becomes quite likely when we made, say, 10 millions of readouts in one single experiment. So we have to change the way we think about probabilities in an experiment. But in order to be able to explain the proper way to report statistics in a high-throughput experiment, I have to start off by telling you how we traditionally report statistics in single readout experiments. So we will start with hypothesis testing and p-values. And once we define that, we could move over to false discovery rate calculations and Q values, and eventually as well posterior error probability calculations of high-throughput experiments. But let's start with single readout experiments and the error sources that we subject ourselves for inside of single readout experiments. And first off, the sampling errors. Most experiments aim at describing a trait or a set of traits of a population. The way we do so is by picking a random sample out of the population. And this sample will be the set of individuals that we do our experiments on, and the ones that we measure this particular trait that we're interested in on. When we do so, we subject ourselves to sampling errors. We might either have been selecting too few number of individuals to be describing the full population, or we might have been selecting individuals in a biased manner so that we select a certain kind of individuals more frequently than others. This is unfortunately not the only kind of errors that we introduce when doing this kind of experiments. We as well have to deal with measurement errors, both in forms of systematic measurement errors due to the fact that our measurement systems might not be well calibrated enough, or different types of sampling noise, random noise. This is due to the fact that our measurement systems might not be accurate enough. We as well have this jargon that we use. We call the variation that we introduce due to the measurement systems themselves the technical variation, where there's the variation of the population, and for that sake as well within inside of the samples are called the biological variation. Frequently one ends up in situations where one would like to compare the status of two different populations. This would typically be a case and control population and case and control studies, or it could as well be patient groups that have been treated or untreated. In any case, it's a great tool to compare two different populations, because we could cancel out eventually measurement errors by, or at least any measurement biases, because due to the fact that we're doing the same kind of measurements on both the healthy and the diseased populations. So I demonstrated here this scenario by somewhat arbitrary example here, where we have defined a healthy population and as well as a diseased population. Each of those populations have a certain feature that we're interested in studying. We call it the mean of that feature mi here for the sake of the argument. And our interest here is to make an inference procedure that could make us a conclusion regarding to the difference in these mean features between the healthy and the diseased population. So the way we do that is that we select a random sample from each of those two populations, and then we measure on those samples, on the sample, we measure the particular trait we're interested in, y, and we as well calculate the mean of that trait, y bar, and we compare those means between the healthy sample and the disease sample. And now we will find a difference between those sample means. And now the question is this difference in sampling and the sample means due to just random noise, or is it actually a true underlying difference between the population means? And so is this difference just explainable by random events? Is this just what we expected to happen, or is this something more fundamental? A very common fundament for making a statistical model that will be able to make inferences regarding the difference between two different populations is so-called hypothesis testing. Here we make two different hypotheses, two different competing hypotheses. First of all, the null hypothesis, that is that there's no difference between the population means, or the alternative hypothesis, the situation where there actually is a difference between the population means. Typically, we're interested in the alternative hypothesis more so than the null hypothesis. We typically want to detect a difference between the two populations, but we still put up this null hypothesis in order to make a better statistical model. It's actually quite hard to know the actual underlying difference between the two populations, and it's much easier to prove make inferences from the null hypothesis. And the way we do this is that we assume that the null model or the null hypothesis is correct, and we then try to assess the probability that we observe a situation as extreme as the one that we observed in our samples. And if this probability become low enough, we're able to reject the null hypothesis in favor of the alternative hypothesis. The far most common way to do so is using so-called p-values or p-value thresholds. And a p-value is the probability that a result was obtained that was at least extreme or more extreme as the one that we observed under the null hypothesis. So actually, we assume that there's no difference between the underlying populations, and then see how likely it is that we obtain two samples that are as different as the ones that we observed, or more different. And if this probability is low enough, or the typical p-value threshold that we use are p-value of 0.05 or 0.01. If this p-value observed is lower than that, we normally reject the null hypothesis and say that the alternative hypothesis is the correct one. One interesting feature that we will be using quite a lot further on in this lecture is that p-values, they are uniformly distributed under the null hypothesis. So it's equally probable to observe a p-value of 0.01 as 0.99. If there is a reason to believe that there's the errors or the differences between the two samples is normally distributed, there's a very easy test for assessing p-values from measurements, and that's called the student's t-test. It's by far most commonly used test for calculating p-values. So the t-test, it uses a test statistic known as the t, and it looks at the difference between the sample means, and it compares that or calculates the fraction between that and the standard error of the difference of the means. And this, if you inject this into a t-test calculator, it will return a p-value to you. A larger t normally is associated with a lower p-value, so the larger t are, the more significant your test is. It's worth noting that the standard error is something that the standard error of the difference of the means. It's a decreasing function with the sample size. So given that you have a if you want to have more power in your test, or if you believe that there's an underlying difference that is bigger or that exists, then if you increase the sample size, you get a larger t, which gives you more significance as well. So your test becomes more sensitive if you increase the sample size, and this is a common theme for all tests actually. So you obtain statistical power by increasing the number of samples. So the student's t-test, it assumes that the differences between the features of or the differences between the sample means is normally distributed, and there are variants of the student's t-test that are including tests that harbor unequal sample sizes and unequal population variance and paired samples as well. There's easy tests out both online and inside of, for instance, in Excel. They're pretty easy to use and hence become sort of a standard for testing. There is as well a nice expansion of the t-test into an ANOVA, or the analysis of variance. An ANOVA test can take more than two populations in account, or expand it to 3 or more variables as well, or 3 or more populations as well. It can as well take dependent variables in account, or a time-dependent variable, for instance. So it's a little bit more flexible than the t-test itself. Just as the t-test, it compares the variance within the sample group with the variance between the sample groups, and if the variance between the sample groups is found significantly larger than this variance within the sample groups, we find ground to conclude that we can reject the null hypothesis. There are, of course, a slew of different other tests that you can do in order to calculate p-values. I will not have time to cover them here. We will come back a little bit later on how we can do non-parametric p-value calculations further on, or later on in the presentation. So let's just turn back now to the random or the statistical inference procedure that we outlined before. We have two populations between healthy and diseased populations, and we want to make an inference regarding one particular trait in these two populations. And the way we do this is by withdrawing sample from each of the populations and measuring this particular trait that we're interested in on the different samples. Okay, so what if it's more than one single trait that we want to study? What if there's a set of n different traits that are occurring here, and would this make any difference to our procedure? We actually say that those n traits, we actually would like to make n different inferences, because each of those traits might or might not be different between the healthy and the diseased individuals. So we end up in a situation where we make multiple tests. Would this make a difference at all? The answer is yes. It actually makes a big difference if we just are comparing one thing at a time or many things at a time. And this is what we call the multiple hypothesis correction that we have to make. Okay, but before we make any further assumptions about multiple hypothesis correction, let's look at the motivating example. So this example I found a couple of years ago in Nature. was a pretty extensive study where one of the parts involved a microarray study of 2 different mice populations. They had compared the transcription level between large probe sets of genes, and they found that a pretty large number of probes were found differentially expressed. So they had measured quite a number of differentially expressed genes. They for different p-value thresholds, they found different number of differentially expressed genes, and for instance a p-value of 0.05, 2,500. That sounds pretty impressive, right? 2,500 different differentially expressed genes. That's this surely is a difference between those 2 populations, right? No, it's actually not true. And the reason why is that, well, if we just start to calculate how many probes would we expect to be significant on the null hypothesis, assume that there are 52,000 probes or on this microarray, then that is that we do 50,000 comparisons. How many of those probes would we expect to be significant under null hypothesis? Remember now that the p-values, as we said before, are uniformly distributed under the null hypothesis. That means that all p-values are as probable to observe. Under such conditions, it's just to multiply the p-value threshold to find the number of p-values that we expect to go above a certain p-value threshold. So for a p-value threshold of 1 per milli, you will find 50 probes that are differentially expressed. And actually, if you use a p-value threshold of 0.05, you'll find 2,500 p-values that are differentially expressed. Now, if you compare that to the 2,492, you actually find less differentially expressed genes than you would expect, just by chance. So this is obviously something that's been flawed in this study. Now, I must emphasize that the author of the study had made plenty of other evidence to back up their findings in other experiments, but I wouldn't trust this experiment at all. This part of the experiment at all. Okay, so how do we compensate for the fact that we are making multiple hypotheses? So measures like the p-value, they account for situations where we conduct one hypothesis test. But the probably easiest compensation for making multiple hypothesis corrections is so-called Bonferroni corrections, where you divide a new error rate or a family-wise error rate with a number of tests. So if you want a family-wise error rate of 0.05 in an experiment that contains 50,000 features, as we had before, well, we have to assess an individual p-value threshold, which is now 0.05 divided by the number of tests, 50,000, ending up with a p-value threshold of 1 part per million. So we have to literally make an experiment that's once in a million. Now you should as well stress now that Bonferroni corrections are extremely conservative. So one should be a little bit careful when using them. There's actually a better way to calculate or to make multiple hypothesis corrections. That's to control for false discovery rates instead of p-values. And I will use the next couple of slides to describe the false discovery rate. So first of all, what is a false discovery rate? So say there's a given scenario here where you've got an oracle at hand that has told us which of our measured traits that are generated under the alternative hypothesis and which are distributed under null hypothesis. We as well have recorded the p-value of each individual trait and sorted them in ascending p-value order and put up a threshold here in this list of hypotheses. And if we now would have for this particular threshold, we record that there are 2 out of 10 of the hypotheses that are generated under null hypothesis. Now the false discovery rate would be the expected fraction of tests that are below the threshold x that are generated under the null hypothesis. So if we would repeat this experiment over and over again and found that 2 out of 10 in average are above this threshold, we would conclude that the false discovery rate of this particular threshold is 20%. So far it's quite easy, but remember now that nobody has told us actually which hypotheses that we are going to test are going to be generated under alternative hypothesis and which are to be generated under null hypothesis. So that's for us to assess. And how could we do so? Well, one of the keys are to assume a mixture model here. We assume a mixture model between the hypotheses that we're using. So we recognize that some of the hypotheses some of the features are generated under the alternative hypothesis and some are generated on null hypothesis. So when we observe the probability of a certain threshold, that would be actually composed of two different probabilities, with both the probability of being from the null distribution, or prior probability of being from the null distribution, and the particular probability of this feature under the null hypothesis, plus the probability of actually being from the prior probability of coming from the alternative hypothesis, and the probability of observing a value as high as the current p-value under this alternative hypothesis. So I just like to think about this exercise here a little bit for a second. So we have different distributions of p-values here. So which of the following histograms of p-values would be a likely outcome of a well-calibrated high-throughput experiment? Would it be the scenario A here, where we got a decreasing number of alternative hypotheses that are decreasing with higher p-value, or would it be, or that's actually a scenario for both A, B, and C here, but whereas the null model, null statistics, or rather the p-value stemming from the null model would be uniformly distributed in A, it will be increasing for higher p-values in B and C. Whereas, and as well, it will be exponentially increasing in the scenario of C, rather than linear increasing as in B. So which one of those three scenarios do you think is the most likely outcome of a well-calibrated high-throughput experiment? The answer is A here. And here we have made use of the fact that p-values are uniformly distributed under the null hypothesis. So any value between 0 and 1 will be as equally probable to observe, and hence we're likely to obtain a distribution just like the one in A here. So for any given part of this probability histogram, we are seeing a mixture between alternative hypothesis and null hypothesis. So in the following couple of slides, we will use this property, the even distribution of the p-values, to calculate the false discovery rate as a given p-value threshold. To show you how to do that, I will follow the nomenclature used in Story and Tibshirani in their 2003 paper in PNAS. I highly recommend you to read the paper itself and have it side by side here of my presentation, as it contains more details about the actual calculations. But so see this just as an introduction to how the calculations should be read. Just a couple of notes of the nomenclature here. The setting is that we have a p-value threshold T, that all the true nulls above this threshold are called f. There's a function f, and above the same threshold, the alternative hypothesis above the same threshold are t, and f plus t is equal to s, the number of the total number of p-values above the same threshold. And if we look on the total number of p-values in our whole experiments, they will be equal to m, where m0 stems from the true null or the true null hypothesis, and m1 from the alternative hypothesis. Not shown here on the slide are as well two prior probabilities. The prior probability pi0 standing for the prior probability of confirming to the null hypothesis, and pi1, which is the probability of belonging to the alternative hypothesis. So we want to calculate the false discovery rate. That's the expected value of the fraction of null p-values above the threshold, score threshold, and so that's the expected value of f divided by s. And this, in fact, is not a new idea in itself. It stems from Benjamin and Hochberg, but here they as well have introduced a couple of new things to this false discovery rate calculation that pays off a bit to the end. So once again, we got m different p-values. Say that we have ordered them from the smallest to the largest one, and for any threshold now, we can say that you can of course calculate the number of p-values above this threshold. That's just to observe and count the p-values. While the false discovery rate now is the fraction between now the number of null p-values of that divided by the total number, we can see that for evenly distributed p-values, we can, of course, the evenly distributed p-values under the null hypothesis, that is, we can calculate f of t as the number of null p-values in total times the score threshold itself, just as we did when we calculated the number of expected p-values above a score threshold for the microarray experiment. So f of t, that will be well estimated by m0 times t, which as well equals to this prior probability pi0 times m times t. So that's calculating false discovery rate, or at least an estimate of the false discovery rate based on the observed p-value distribution, would just now be equal to an estimate of the pi0 times m, the number of the total number of p-values, times this score threshold, and divide that by the number of p-values that we observed above the same threshold, which is an easy task to calculate. So we have to come back to how exactly to calculate this factor pi0 later on in our slides, but the m is known. That's simply the number of statistics that we are looking at, the number of p-values that we have been taken into account, and t is just the p-value threshold itself, and we can of course count the number of p-values above the same threshold. So just a graphical illustration of the same phenomena. So our estimate here of the false discovery rate will be now just the area, the number of null hypotheses divided by the number of the total number of hypotheses above this score threshold. So this will be the red area divided by the green plus the red area. And this is the red area here is just calculated through the fact that the null p-values are evenly distributed all over our run, or all over the 0 to 1 area. Okay, so how do you calculate pi0? Well, the prior probability pi0 would be technically equal to now the number of, or it would be very well estimated by if we could in some way calculate the area of the under the curve here of the red distribution, or and just divide that by the total number of hypotheses in total. This is a little bit harder to do than it looks like. So inside of the story Tibshirani paper, they instead look on they twist the problem a little bit, and they say that they take more interest in calculating the number of p-value above a score threshold at this time. So they check the number of p-values above the threshold, and they compare that to the total number of p-values times 1 minus this p-value threshold. So this would be taking this blue area above the score threshold and divide that by the total number, that is the blue plus the yellow area here, and times itself the p-value threshold minus 1, or 1 minus this p-value threshold. Why do we do this? Well, actually, of course, we want to estimate this for as a high p-value threshold as possible. The closer to 1 we select lambda here for estimate, the more close we will be in theory to the pi 0. However, the closer we get to 1 as well, the more subject we are to variation of the p-values. So there's a trade-off, there's an optimal trade-off here between having a high p-value, being more accurate, and sort of taking the variation of the p-values in account. And the way they solve this in the article, at least at a couple times, is that they calculate pi 0 estimates for all different for a whole set of different lambdas, and then they fit a third degree polynomial to this this distribution, and see where that third degree polynomial hits the lambda equals to 1, and make that as the pi 0 estimate for subsequent calculations. Storer and Tibshirani as well go on to define what they call the Q value. That is the minimal false discovery rate that includes the current p-value. So it's a way to ensure that we get an individual false discovery rate for each individual p-value, as well as we're seeing to that we get an increasing or a monotonically decreasing function with a threshold. And this is useful because otherwise we would have multiple sets that would include the current p-value, but we just select the one that currently has the lowest false discovery rate as the definition for the Q value. This is in some way in an analogy with the p-value itself. In some situations, it's possible to derive false discovery rates in an alternative fashion than to derive explicit p-values. And this is the situation when we actually have a so-called null model, or a mechanism that generates experimental readouts under null hypothesis. This is, as I will show a little bit later on here, quite frequently the case that we can produce such a mechanism. But if that's the case, we can generate p-values quite easily by just checking the number of null hypotheses that goes, or null readouts that goes above a certain score threshold, and or the score threshold that we're interested in. This serves the purpose of actually this facilitates us now to calculate approximation of the false discovery rate just by measuring the number of null statistics that goes over a certain threshold, and we divide that by the number of actual statistics that goes above the same threshold times pi 0. So just to make an example of this where this happens, say that we have been measuring the difference between two samples in each in both in the healthy and the disease population that we were talking about before here. Well, we could create a forward statistic or a normal statistic here by just comparing the differences in or the sums of the healthy samples minus the sums of the disease samples. But we could as well now create an explicit null model from the same data points by creating a mechanism, a small set here, which would be defined as the difference between the healthy samples with addition of the difference between the disease samples. Both statistics will, or both the little set and big set now will be representative readouts from experiment, but whereas the null, whereas we expect the null hypothesis and null statistics here just to be representative of incorrect readings. There's no reason to believe that there's a bigger or smaller difference between the samples for any kind of readouts. So another example of this kind of explicit null model is inside of database search engines in shotgun proteomics, which I will cover in a later lecture. In such a case, we have an explicit decoy model that stems from scoring already known incorrect peptides against spectra, and compare that, and that would be your explicit null model, and we call that a decoy model as well. And we can compare those scores against scores from matching real peptides or target peptides against the same spectra. So that will as well be a valid scenario where we directly can evaluate the false discovery rate just from a set of scores. But it of course requires us to have an explicit null model in the first place. So lastly, I would like to introduce you to yet another concept, and that's the posterior error probability, or this is also known sometimes as local FTR. And this, the posterior probability is the probability that a particular identification with a certain score is incorrect. So that will be the case, or generated under the null hypothesis, that is. So this is an analog with the QL itself, or the false discovery rate itself. Remember, before, when we were defining the false discovery rate, we were comparing this green area here above the threshold. In the graph below here, we used the red area of the null hypothesis and related that to the summed area of the green and the red area. That was our false discovery rate. The local false discovery rate is just for the particular threshold, so it would be the right-hand border of those areas. So we will then compare the difference in height between the red areas, right border here, with the total length of the red plus the green area. And this will be our posterior error probability. This is a bit cumbersome to derive in practical terms, because the p-value distribution will always be a little bit jagged by the actual observed set of observabilities due to the random effects that occur. So any posterior error probability estimator will have to include some smoothness process where you have to use a lowest filter or a spline fit or any kind of operation that will smoothen our observations to obtain an even distribution of samples in order to derive the posterior error probability. So it's always be somewhat tricky. Then we can rely on different types of softwares to do this for us. So why do we need these different issues? Well, just to drive this home again. Well, false discoveries in Q-values, there are good when we will identify sets of significant readouts. So they're typically interesting when you have a set of identifications that we want to identify. This could be when our downstream analysis involves, so say for instance, enrichment analysis or something, or pathway re-enrichment analysis, or something where we are interested in actually identify sets of identifications. However, if we take interest in a particular readout from a high-throughput experiment, it might be more valuable actually to investigate the posterior probability, because that would be more directly focusing on the property of this particular readout. So if you just want to make one readout from a high-throughput experiment, check the posterior probability of that readout. And a P and E value of an experiment, that should be solely reserved for experiments where we render one single readout. This is very seldom the case for high-throughput biology, so I would advise you to never use a P or E, report P or E values for any high-throughput experiment. This concludes my presentation for today, so thank you for your attention.